Now, I think, folks, with that, it's time we begin. So I'm thrilled to roll out today the latest episode of the IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic communities. And I'm your host, Zlatko Minev from IBM Quantum Research. And today I have the pleasure of introducing Shay Hacohen-Gourgy. Shay received his PhD from Tel Aviv University in DC transport measurements at low temperatures with a background in superconducting and magnetic materials. Shay then did a postdoc at Irfan Siddiqui's lab at UC Berkeley, my alma mater and alma mater group, and has since then moved on to found a new circuit quantum electrodynamics lab at Technion, Israel. The lab's major interests are in improving and exploring the physics related to superconducting circuits, improving the circuits themselves for quantum information, and utilizing their capabilities for unique quantum control. Shay, it's a pleasure to have you here. How are you today?
I'm doing great. Thank you for inviting me. It's very nice to be here. Yeah, and I'm tuning from Israel near Haifa.
Awesome. Well, I hear from you that you're a regular listener here because you anticipated my next question, which is where are you tuning in from?
Oh, yeah. Well, I heard the introduction, but yeah. Yeah.
Awesome. Well, folks, I'm about to hand it over to Shay. Just remember, since it's a new year, this is a very interactive forum, so feel free to ask questions of Shay. In fact, he told me he encourages more discussion and interruptions. So post those in the Slack channel as we go. And with that, Shay, the stage is yours.
Okay. Well, thank you, Zlatko. Okay, so today, like Zlatko introduced, I'll be talking about universal control using the quantum Zeno effect. This is I'd like to say this is our latest work, but this is really the first work from our lab. We're a relatively new lab. The slides are not moving. Oh, there we go. So we're a standard circuit QED lab, relatively new. So this is the first work we've put out. We have, 2 dilution refrigerators. We make our samples, put them inside, send in some microwave signals, have them reflect back up, look at the signals, process them, and so on. And these types of labs, you've seen many of these experiments in these talks and other talks. These types of labs typically deal with two different things. One is quantum information processing related mainly to quantum computing and technological things and so on and so on. But also related to fundamental physics, really deep fundamental physics. And the work that I'll talk about today sits kind of somewhere in the middle between these. So there'll be a gate here and it'll be reminiscent of quantum information processing, but it really touches up more on the fundamental physics and quantum mechanics and things like that. And the idea of this work, of this universal control is, so we want to realize universal control in a non-interacting system using the quantum Zeno effect. And what do I mean by universal control in a non-interacting system? Suppose that you have some system of many qubits or many spins or something like that, and all we have is local control. So we can manipulate each qubit individually, and there is no interaction between them. What we're going to see is basically by observing part of the system, observing it really, really strongly, and we'll define exactly what that is, but we're going to call that a Zeno observation. We can induce universal control. Universal control means that we can create any state that we want within that system, or we can apply any unitary within that system, any evolution within that system. But before I start with the experiment and what we're doing through, I want to start off with Zeno. Where does Zeno come from? Who is Zeno? So Zeno was a philosopher. He's from Elia. I hope I'm pronouncing the name of the town correctly, but it's a town in near Naples in Italy. And he lived around 500 BC. And he belonged to the Eleatic school of philosophy, which was founded by Parmenides. And this school, and Parmenides specifically, they believe that motion is an illusion, really. And Zeno was he was Parmenides' most enthusiastic disciple, really, and they were contrasted by the views of Pythagoras and Heraclitus, who believed in quote world of change. Okay? And Zeno basically spent his whole time trying to prove that motion is an illusion. Now, back then, you didn't really have contrast. You had contrasting views, but there was some higher people, Plato and Aristotle in that case, who decided who's right, who's wrong. And Zeno really never wrote down his work, or we don't have any recollection of his written work. What we know about Zeno and his ideas is basically from Plato and Aristotle's writings themselves. And in their writing, they describe Zeno's ideas that were meant to prove that motion is an illusion. Basically, Zeno wrote these paradoxes, which were, and I hope I'm pronouncing it correctly, reductio ad absurdum. It means basically ridiculing the ideas, trying to make something sound ridiculous in order to contradict this. And a lot of us are familiar with these famous paradoxes. Those one, the Achilles and the turtle, where there he tries to prove that there is no motion by this story, which if you tell it to a little kid, it makes sense actually. So think about Achilles and the turtle. Achilles moves fast, and the turtle moves really, really slow. And the paradox is that if the turtle starts first, Achilles will never actually catch a turtle because it takes Achilles some time to catch up to the position where the turtle is right now. And in that finite amount of time, the turtle will move a little bit forward, and then Achilles will need to catch up to that. And that is a finite amount of space. And in that finite amount of time, the turtle will move a little bit more. And forever, Achilles will never actually catch the turtle. Another similar paradox to that is the dichotomy paradox, where if you need to get to point A from point B, you always have to cross the middle. And there are infinite middles, and if it takes you a finite amount of time to reach each middle, then you will never get to the end point. And the idea was that summing up infinite things comes to infinity. Now, these ideas were actually solved by infinities, and now we understand that it is actually finite, and Achilles will catch the turtle. And the third one, and this is the one that I gave this kind of funny cartoon up here that I found online, is the arrow. And the arrow one, well, so these first two paradoxes really kind of dissected space into little parts. The arrow one kind of like tries to deal with time, and it says that if there's an arrow, and this is the paradox that really relates to the quantum Zeno effect, if there's an arrow and it occupies a certain position in space, and it occupies that space at a certain time, then it's just there. It's not moving away from there, and it's not moving to that point, it is just there. Hence, it is not moving, and motion is an illusion. Now, Plato and Aristotle in their writing, they really didn't like those claims. And they're writing it in the way that kind of discards their ideas. And over the years, we really understood that Zeno's ideas were wrong, really. And this notion of motion is an illusion kind of failed, okay? And I really like this cartoon kind of, this is why I put it up with, I guess this could be Plato or Aristotle holding the arrow here and asking Zeno, are you sure the arrow won't hit you? Okay. But the main point here that I want to put across is the ideas of Zeno that took about 200 years to understand. And his real belief, true belief that motion is an illusion. Now, this was kind of like regarded and put away for a while until the Zeno's paradox came up, again in quantum theory by this rather seminal paper by Misra and Sudarshan. And they talked about a quantum system, a two-level system. And what they wanted to show, a little bit like Zeno's idea, is that if you look at something, and this is this arrow occupying a certain space at a certain time, if you look at it hard, it will not evolve. Now, in quantum systems, what happens, or in a quantum two-level system, what happens is you have this atom, a two-level atom, and at very short times, there's always some short time scale where the evolution is parabolic. And over that, and at those times, if we now apply rapid projections, okay, projections at a rate which is faster than that quadratic time scale, then what happens is the system will always collapse. Okay, the back action of the measurement will collapse us to the initial state, and the system will not evolve. Or if you're measuring really continuously, really hard the system, then the evolution between state 1 and state 2 will slow down. And this is kind of the notion of a quantum pot will never boil. Okay, and some people do say that they can feel this. Some mediums will say, you know, I'm watching my pasta and the pot never boils, but that's a whole different story, of course. My slides, oh, there we go. So about 12 years later, came a very nice work by Dave Wineland's group, and they really demonstrated this this quantum effect for the first time. They took a beryllium atom, and they used the two levels of the beryllium atom here, labeled as 1 and 2. So this was their two-level quantum system, and they drove it with an RF transition. So if nothing is happening, then it will be Rabi flopping. And then they use the third level to apply projection. So it's a slow Rabi flopping, and every certain segment of time, they're applying a very fast rapid measurement. And what they saw is really the inhibition. So if the system was started either in state 2 or in state 1, the evolution from state 2 to state 1, or from state 1 to state 2, was slowed down by these rapid projections. Now, this paper got a lot of attention, not only because of the experiment. Really, there was no argument with the experiment and the results of the experiment, but it got a lot of attention basically because of this sentence and the way things are phrased in that paper, and that is, inhibition arises because the measurement causes a collapse of the wave function. And people took this as trying to prove that there is wave function collapse. And back then, and still now, there's a lot of debate of what is quantum measurement? Is there wave function collapse? Is everything unitary? And so on and so on. And I think these debates still go on. And the Zeno effect, what is nice about the Zeno effect, his philosophical ideas still kind of like take us on to philosophical discussions of quantum measurements and wave function collapse and things like that. There is even a whole comment written about this paper that takes the experimental results and analyzes them without any measurement at all. Of course, we can always keep track of our degrees of freedom and see, you know, that we can keep our wave function unitary, and there is no need to induce any measurement in the system, and the results will be the same. That was the claim. This is not a proof of wave function collapse, and the debate still goes on till today with these philosophical discussions. So we're going to fast forward a few decades later, and the discussion that we had till now was about two-level systems only. Okay, so we have a two-level system, and what happens when we observe one of the states of this two-level system, that basically inhibits the evolution of the system. And now what happens if we take a larger quantum system and we're observing part of that system? So we're applying some projector, this is P, and that projector is measuring part of that Hilbert space. You can then describe this evolution by what is called the Zeno Hamiltonian. And there was a lot of work by Pascasio and Facci and so on over the years, showing basically that if you have some trivial coherent evolution, if you observe part of the system really strongly, meaning, you know, infinitely fast, rapid projections, or an infinitely strong continuous measurement, then you're inhibiting evolution to part of that Hilbert space, and then you get complex evolution in the remaining, what is referred to as a Zeno subspace. Now, an interesting point in time is, wait, something is there, okay. An interesting point in time is 2014, so that's not long ago, that's about 8 years ago, I think. Came out three really nice papers, 2 of them experimental, those are the ones that I'm showing over here, and another theory one, which I'll talk about in the next slide, that demonstrate these quantum Zenodynamics. The first paper here on the left, this is the one by the group of Serge Haroche, and they titled it very nicely and connected it to Zeno and his arrow, called Confined Quantum Zenodynamics of a Watched Atomic Arrow. And the other experiment is quantum dynamics of electromagnetic mode that cannot contain n photons. These experiments are very similar in nature. In essence, what is happening on the left one, it's basically an atom that is put in electric field, and it basically acts as a giant spin. So if you have a giant spin, you can describe its state on a giant block sphere, and you can live, and they applied a certain drive that blocks its evolution out of that space. And this is what is, and here there's a plot of the Wigner function after a while. On the right one, I'll explain that one, and maybe we'll make the left one a little bit more clear. On the right one, there's a similar system. There is a harmonic oscillator, so many levels, and it's coupled to a superconducting qubit. So this is a system very similar to the system that I will talk about today. And if you just take a harmonic oscillator and you drive it, you will get a displacement, meaning that you will have a vacuum state and it will just displace up, or you will climb up the ladder of levels. And what they did in this rather beautiful experiment here is they added a drive which essentially splits the third level of the harmonic oscillator. And this splitting put the 2 to 3 level transition off resonant, such that if the system starts in the ground state, if you drive it, it will start evolving like a harmonic oscillator, so it will be displacement, but then it will hit the certain wall. And this is this dashed line over here in the Wigner function. This is this dashed line. And so the coherent states kind of hits this wall and evolves. And after a while, well, you can see developing these little fringes, these blue spots, which are negative parts of the Wigner function, which is showing that something non-trivial or complex is happening. Okay, so these 2 experiments really show that you can get coherent dynamics, but which are complex within the Zeno subspace. Now, in the same year, another very interesting paper came out by Daniel Burgarth, who is also part of this work, and Pascal Yosefario and this group over here. On the mathematical level, what they showed is that if you have one Hamiltonian and another one and they commute, this does not imply that PHP, the Zeno Hamiltonians, do commute. And this leads kind of like to the complex evolution, but what they showed is even more interesting, and that is that such a system actually gains universal control. It's not that the evolution becomes more complex, but now you have full control over this reduced Zeno subspace. Right? So if I observe a certain subspace, I now have a certain subspace which I can create any state or do any operation in it. But they also showed the converse, and that is that any complex quantum dynamics can be viewed as the projected dynamics of a simpler one in larger dimensions. Now, this work is nice, I think, also on the philosophical level, because, and again, I want to relate it back to Zeno. I think this work tries to tell us that, and I'll be a little bit provocative. I may get a lot of backlash here, but I'll be brave and I'll kind of say it that I think it shows maybe that, at least on the mathematical level, measurement can be regarded as an illusion. Zeno back then thought that motion is an illusion, but maybe measurement is an illusion, because any evolution, any complex evolution that I can describe over here, I can always take a larger Hilbert space and describe it as a very trivial coherent evolution. Okay, so any evolution can be on a larger Hilbert space will be coherent. So it relates kind of like to a notion of maybe measurement is an illusion. I know it's provocative, but
to kind of play with that a little bit. I guess in a sense that seems to me to be somewhat similar in spirit to saying that you can derive the stochastic Schrodinger equations, or either take them at fact or derive them from the larger system broken up into pieces. One is measured and so forth. But there usually you still need a measurement somewhere down the line or something. Is this somehow equivalent to that, or is it different?
It's very similar. Yeah, this is very related to that. Yeah, you can, and in an even simpler thing, right? It's related to you can always take a density matrix and purify it, right? So whenever you look at quantum things, they look all complicated, you put them on a larger space and it looks simpler. Right? So maybe there's something simpler there. We just don't see it. We can't account for all these degrees of freedom. Maybe we're too stupid to see them. So everything looks very complex, but maybe it's just a lot simpler. But this is philosophy. Okay, so I think that's enough philosophy for today, maybe. And we'll continue to the actual thing. Okay, so this is all kind of like nice and in theory, but what we want to talk about is an experiment, okay? And we want to talk about, so we're going to talk about something that we're going to refer to as the Zeno gate. So we're going to take a specific example, and we want to see this idea of universal control in a very specific example that is relevant, and we can also do and observe in the lab. So, if we imagine a set of qubits and we can locally control those qubits, we want to add some observation to them and see that we can get this universal control. And then we want to see really, when we look at this observation, then we got to ask ourselves, what is this observation and how is this a simpler system? But at the end, this observation is also some quantum apparatus in itself. Okay, and if you consider it quantum, then you see the simpler evolution. If you consider it as a measurement, then it looks like these complex dynamics. And so what I'm going to present to you is the main protocol and the main idea behind this work. So we're going to take the simplest system. This is a qubit qubit system. So qubit GE, these are the states of the qubit, and we have GE and F of the qubit system. And we're going to have a local drive. So we're going to be driving our qubit from the E to F transition. So it basically drives these two levels. And now we're going to be adding a projector, basically a measurement that continuously or infinitely rapidly asks the question, is the system in the FE state? Is the system in the FE state? Repeatedly, always and always. So this is a very strong measurement, asking the system. And if we do that, we can basically calculate the resulting Hamiltonian. And you can understand this intuitively in the sense that when we're driving to the E to F transition, we're cycling these levels over here. And what the measurement is doing, it is inhibiting the evolution to the FE state. So we're just left with the evolution from basically EG to FG. And the idea here now is to gain the universal control. Remember, universal control in a qubit system, we need single qubit control that we have, and we just need to show that we have a 2-qubit gate. And in this case, we're just going to show how to do a CNOT gate. Okay? So if suppose that we initialize the system, so you can see this, if we initialize the system in a product state, in the plus product state, so you do a pi half on each of the qubits, you put them each in a superposition, and what will happen after one oscillation is that the EG state over here will pick up a phase, and so it will pick up a minus sign. And now what we have here is basically a Bell state. And the operation that we've done here is exactly equivalent to a CNOT. Okay? And this is the idea. And if you understood everything I said till now, then you've understood most of the talk. Okay, so from now on, from this point on in the talk, what we're going to do, we're going to expand this to multiple qubits. I'll show you that it works exactly the same. So this is, we show that this operation does a CNOT on 2 qubits. I'll show you that the exact same operation on multiple qubits entangles all those qubits in this single operation. And then we're going to see how to realize this on a real system. So how does this work on multiple qubits? It looks exactly the same. So now we have many, many qubits and one qubit. And what we're going to be doing, so this is the our space. So G, so the first index indicates the index of the qubit. So we have G, E, and F over here. And again, just like before, we're just going to be driving locally the E to F transition over our qubit. So that drives basically all these levels. This is a local drive. But our projector is highly non-local. Our projector is now just going to be observing the FEE state. Okay, it's going to be again asking the question, are you in this state? Are you in this state? Very, very rapidly. So it will inhibit the evolution from the EE state all the way to FE. All the others will not be inhibited. And if we look at the evolution of what happens, so if we have states with G, the qubit starts with G, nothing will happen to those according to the Zeno Hamiltonian. If we now look at states that started with E in the beginning, they will pick up, again, this minus sign phase, okay? Except for the E state, which is being blocked by the Zeno. And if we now look at the resulting state, we can actually show that this is equivalent to an NC-NOT gate. So this is a control. So it's a C-NOT gate that is conditioned on all the qubits in the system except for the qubit, and this immediately entangles all the system. The point is that we had a local drive, but we had a highly non-local observation. Okay, so the measurement has to have information from all the qubits in the system. So when we want to describe the system, we're going to describe it basically with a continuous measurement. I'm sorry, this is getting a little bit technical, but I need to kind of describe it a little bit.
Maybe a conceptual question before that, if you'd like.
Yes.
Yeah, just if we go back to the simple case of the qubit and qubit slide.
Yes.
So to kind of summarize what you said in other words is the measurement is essentially blocking one of those transitions. So instead of a more non-selective transition, you have a more selective transition, and that allows you to basically introduce this phase factor and make an entangling operation. So I guess the other way to maybe think of this is, let's say equivalently I could do this if I could just offset the FE level in frequency and apply that selective drive, I would get a similar interaction, right?
You will get the exact, this is basically similar to what was done in this experiment over here, right? They did some sideband drive, which splits the level 3 of the harmonic oscillator. So it shifts them, and then you're basically blocking that evolution. So you can exactly understand it on that level. Now, the difference is that here, you're actually observing, so you're getting information, did you evolve into that state or did you not? Where if you're just shifting that level in some other coherent way, then it's just not on resonant. Okay, but the dynamics will be exactly the same dynamics as you get from this Zeno Hamiltonian. So both cases, you can call them Zenodynamics. Yes.
Oh, I see. You're saying there you're essentially also doing measurement. You're just not reading it.
Here, well, I don't know where the measurement is. It goes, I think, a little bit to the notion of what is a measurement. I mean, in this specific setup, you would ask, if it's a measurement, then I need to know. And how do I know if there was an evolution or not here? In this case, it's easier for me to know because if the system actually escaped to the FE, then I know that it escaped. So it's easier for me to call this a measurement, where in the other case, I don't know if I can call it a measurement. But if I'm just looking at the dynamics in the Zeno subspace, they're still governed by the same Hamiltonian. So we'd say, I don't care. I care about the Zenodynamics. If you're on the other side, you would say, but this is a measurement and this is not. So, again, the philosophical discussions, you can always go into these things.
Awesome. Very nice.
All right. Okay, so we understand this C0 gate. And so to describe our system, we're going to be continuously measuring the system. And we're going to be describing it basically by the master equation. So this is the typical master equation. This is the measurement rate. Over here, gamma is the measurement rate for the master equation. This is going to be our Hamiltonian. Now you can take this and solve this and calculate the escape, the chance to escape, to get this escape, and you get this. This is an approximation in the case where the measurement rate is much larger than the Rabi drive, which is what you want in the Zeno case. And you can derive from this the jump rate, and this is all results that have been known for many, many years. Now, since you can...
Is it easy to motivate why it's omega over gamma and not... usually in Zeno, you see things like omega squared over gamma, which is the transition probability divided by the measurement rate. That here it looks different.
So this is the probability to succeed. When you're doing this whole 2 pi cycle, this is the probability to escape. You can derive from this the escape, and then you will get the omega squared over gamma that you usually get.
Okay, yeah. That's rate versus probability. Cool.
Yeah, rate versus probability, exactly. Okay, and so, if we have the system and we can detect the escape, then we can ask ourselves, what is the fidelity, okay, of this gate if we're observing the escape? So you can imagine some detector, and there's some detection thing. So you can do like a jump model and say, okay, there was either an escape, and I know that I'm in the FE state, or there was no escape. And if there is no escape, then you can calculate what the Hamiltonian is, and this is the Hamiltonian. And you get this term over here, and now you get this dephasing term, because if time goes by and you see no escape, then there's a decay of the FE state, so you get this non-Hermitian part. You can calculate what happens to the wave function. You can see that the GG, GE, and EG states do what we expect them to do. See, this one here picks up a phase after the 2 pi cycle. The thing that might be a little surprising here is this part. What happens to the EE state? We can see that the EE state, despite being blocked, because the measurement rate now is finite, it is not infinite. What happens is we're observing the system, and it's not that nothing is happening to the EE state. The fact that there was no jump, there was no escape, means that maybe there was no escape because there was no population in the EE state to begin with. And so there's some dephasing. So by the fact that we're not measuring we're measuring FE, and there's nothing going on, we're getting information about EE. So there's a little bit of dephasing, okay? Because there is some chance for escape, we're getting some dephasing on the EE state. So this is a little bit surprising, and this is what leads to this kind of, so, if you look at a heralded fidelity, you would expect, okay, either I can detect an escape and it failed, or there's no escape and it didn't fail. But no, at finite measurement rates, you will get this decrease in fidelity because of this dephasing of the EE state. And also this you can approximate a little bit and get this dashed line and get these nice analytical formulas which were calculated by Lee. Okay, so now we get to the meat of the talk, I guess.
We have maybe one question from the audience, if you would take it. So I swear I did not ask this question. This is from Kelly from the audience. But does this setup enable monitoring for signals of a jump akin to the Devere's Lab 2019 to catch and reverse a quantum jump mid-flight? Which is my paper, but not my question.
It is your paper. I guess your paper, your mid-flight paper, is closer to the Dave Wineland paper, right? Because you have a two-level system and an auxiliary system which you're driving, and your paper is mostly similar to this, like in the level setup.
It's a V-shape demo electron shoving readout scheme.
Yeah. But in a sense, yeah, you could try to monitor it, but as you will see, we will talk about the discrepancies in the different things. But here you cannot quite catch the jump, and we'll see that really towards the last slide. We'll see the problems of why you cannot catch the jump. The parameters of the system won't allow you. Basically, in your system, you were monitoring very, very fast, rapidly. And here, in order to do the Zeno effect, you will see that the line width of the cavity needs to be rather narrow. So the jump occurs, the jump is basically averaged over this. We'll see this in the following slides.
Awesome. Thanks. Looking forward to it.
Okay. So how can we realize a system with such local control and non-local measurement? And well, to realize this is really the typical circuit QED setup. So, you know, a lot of people like to work with atoms and lasers, but we just don't have the protective glasses, and I have no idea how to catch atoms. So we go with our circuits and manipulate them with our microwave signals. And we're going to use everyone's favorite circuit. I know Fluxonium people are saying, no, Fluxonium is now favorite, and everyone has their own flavor. And they're like, no, that is now the new favorite, but I think Transmon is still the favorite. So we'll go with that. And not only are we going with the Transmon, we're going with the classic coffin-style cavity. I hope coffin style doesn't mean that it dies at some point, but I really like this setup. It really has this historical stance. It really kind of broke the field in the coherence barriers there. Okay, and for those who are not familiar with the Transmon, I'll just give 30-second, 1 minute about the Transmon. So the Transmon is basically an artificial atom. It is the qubit. It is the most popular qubit. It is used by most groups that are building quantum computers, IBM, Google, whatever. Maybe I'm not allowed to mention Google here. I don't know.
That's all right. We had some folks from there speak here.
Okay. It's a joke, of course. Yeah. And so the circuit of the Transmon is basically a Josephson junction, and it is in parallel to a capacitor. It sits here right in the middle of the cavity. It has these two. So this is basically aluminum. Aluminum on a piece of silicon. The two paddles over here play the role of capacitors. They also play the role of two little antennas. So that's how the Transmon couples to the electromagnetic field in the cavity. In the middle here, there's a wire. And if you zoom in, there's a little crisscross, which is the Josephson junction, which is just a sandwich of aluminum oxide and aluminum. The nice thing about a Transmon, except for its coherence properties and it's a great qubit and so on, is that it's a slightly unharmonic oscillator. Basically, the parameter regime is such that the capacitor is relatively large, such that EC is much smaller than EJ, and we can take this cosine, develop it in series, and then we get the phi squared basically from here. That forms the harmonic oscillator, and the next term gives us a small correction to the unharmonicity, which means that it's relatively easy in the system to access the few first levels and the first even 4 levels have been studied for coherence properties and so on by several groups. And it's relatively common to use not only the 2 levels, but also the 3 levels. So for our experiment, we need a qubit and a qutrit, and we're going to be using basically 2 transmons. One is going to be our qubit, and the other one is going to be qutrit, where for the qutrit, we'll use the first 3 levels of the transmon. Okay, so we're going to have the 2 transmons, and the cavity in the setup, so sometimes the cavity is used as a whole Hilbert space, in bosonic encoding and things like that. And in many times, the cavity is used in common experiments as a measurement apparatus, and this is also going to be the case here. So the cavity is going to be the tool that will give us the known local projector that will measure the state of the 2 systems. And again, for the experts, this is kind of known, but for those who are not experts, I'm going to go through how this works, really. And the idea is that, so we're going to look now at a single qubit, but this will carry on also to the qubit and qutrit system. We have our qubit in the cavity, and it's got these little antennas, so it has got a dipole coupling to the electromagnetic field, and it forms this Hamiltonian right over here, cavity, qubit, and the coupling between the 2-level system, the qubit and our field. Take the typical rotating wave, the usual rotating wave approximation, and you reach what is called the James-Cummings Hamiltonian. Next, you basically, the frequency, the transition frequency of our qubit and the transition frequency of the cavity are going to be far away from each other, compared with this G parameter over here. And that will put us in what is known the dispersive approximation, which is given here by this Hamiltonian. Now, what is nice about this dispersive approximation, what is nice about the system with the transmon couple is you can get relatively strong couplings such that the dispersive shift between the states is larger, much larger than the line width. So this Hamiltonian can be viewed basically as our qubit and as a harmonic oscillator, which has two distinct frequencies which are separated by this parameter chi. And for a qutrit, there will be 3 peaks. So there will be G, E, and F. So this is all near the cavity frequency. And this chi can be tuned, in experiments, it's tuned from, kilohertz or even all the way down to nothing to several megahertz. And this is going to be the key point, the key mechanism to doing the measurement. The idea is this. So if we consider the following setup, so this is just a pretend mock setup. We have our qubit in the cavity, and we're going to add to this Hamiltonian, we're going to add a drive. And this drive is going to be at the frequency of omega g. So the frequency of the cavity if the qubit is in the ground state. And if the qubit is in the ground state, we're going to get a large signal transmitted through the cavity. And if the qubit is in the excited state, we're going to get basically almost nothing. We're going to see vacuum. And this is kind of what it looks like. So you would see like basically a voltage as function of time, and it would average out to 0 if you're in the excited state and to something if you're in the ground state. Okay, so we can apply a tone at a certain frequency to know if the qubit, what state is in the qubit, and that's how we apply the projector. This is kind of what it looks like. So this is the IQ plane. You can see the display state in the case of the ground state, and the vacuum state in the case of the excited state. The measurement goes through a JPA, so there's a whole amplification that goes on here. Okay.
What's the kappa in all this?
Kappa? Yeah.
Right.
So yeah, kappa is 150 kilohertz. I'll get to that in a moment. And this brings me to the next point. The important thing about a qubit measurement is usually we regard it as we set up the qubit in a certain state, and then we're just measuring it. Okay, and the assumption is that the qubit is not evolving during this measurement, and this is an important assumption. And So basically an infinite kappa in that sense. And if the qubit is not evolving in that measurement, then you can relate the measurement rate to the drive strength by this relation of kappa and epsilon. If the qubit is evolving, suppose that you're Rabi driving the qubit during the thing, then this relation between gamma and the drive strength doesn't hold anymore. It becomes a little bit more complex. And this is what's going to happen in this experiment, really. But if the qubit is not evolving, then this is the relation between the ratio between epsilon and kappa. So if the Rabi drive is very, very slow with respect to kappa, you can take this as a reasonable approximation. If it's not, then it doesn't work as well. And we're going to see that in a moment. Okay, so let's look at our experimental setup. So we have our cavity. It has a qubit. This is this one over here, and a qubit. They're designed so such one that is sitting at around 3 gigahertz. The qubit is sitting at around 6.2 gigahertz. The different size paddles over here are designed so chi's are the E to G chi's of the two qubits are almost identical. Okay? And the limiting coherence times in the system are going to be the coherence times of the F state. So the F state, the F2E transition of the qubit was about 13 microseconds, and the Ramsey time of that transition was about 5.8 microseconds. So these are the shortest coherence times in the system, and they're going to be limiting. And the cavity, we have a strongly coupled pin, which gives the kappa, which is about 150 kilohertz. And
could you just say why qubit 1 was rather so low in frequency?
The qubit?
The qubit.
Yeah, we want them far away each other from frequency because we want them non-interacting. So you want to suppress the ZZ interaction completely. In this case, it was, I think it was about 25 kilohertz.
Mm.
So negligible on the time scales of the experiment. Okay, so we purposefully designed them to be far away in frequency, but we adapted the pedals such that chi's are going to be the same. Remember, we want a non-interacting system. This is the main point over here. So let's look at our experimental scheme. So we have our system. This is the dispersive Hamiltonian. So we have chi1, E1, chi2, E2, and chi-F. And the idea is to drive the E to F transition, which sits somewhere around 3 gigahertz, while applying a strong tone at omega Fe, basically the transition of the cavity frequency, which corresponds to the Fe state. And the idea is that if we now drive it, if we see a transmission through the cavity, we know that we're in Fe. If there is no transmission, we know we're not in Fe, and this is how we're xeno-blocking our system. And apparently this looks very nice. You can just apply it, and it should work. But really, the scheme is too naive. Okay, this is not the full story, and there are two important things that we need to consider here. One is the finite cavity line width, and two is something called a rip gate that evolves. And for those experts, they can already understand what is going to go on here and how we're gonna, and I'll show how we're going to deal with that. Okay, so the finite cavity line width really deals with the fact that the measurement, our measurement rate is only correct, or the measurement rate relates to the drive strength only in what is called the Markovian limit. Basically, if the evolution of the Rabi drive is very slow, but we don't want it to be too slow because we're also limited by coherence times. Okay, so let's see how this works out in experiment. And what we're going to do, we're going to look at the Zeno effect on a two-level system. So we're going to look at the GE transition of the qubit. So what we're going to do, we're going to Rabi drive the qubit, and this is the blue line over here. So this is just regular Rabi oscillations. And now in another experiment we add a small, call it a weak Zeno drive. Maybe an oxymoron, but just a very weak drive. And we can see the green line, these are basically dephased Rabi oscillations. This dephasing occurs because of the measurement. So this is basically measurement-induced dephasing. And if we now apply a very strong drive, what is happening is basically the system is now being completely damped due to this Zeno block. So basically the system is trying to jump, and at some point it jumps and it gives this exponential. Note that if there is an escape, there will not be a return. So if the system started in G, if it did escape to E, it will not return, because as soon as it escapes over here, the cavity populates with a lot of photons, and that causes a Stark shift or a light shift, and now the drive is going to be off-resonant, highly off-resonant, and the Rabi drive can't bring us back from E to G. And this is why we get this kind of like curve, and it will never jump back.
I guess eventually T1 might make it come down and in return.
Yes, T1 will come, yeah. But T1 here is, I don't know, it was like 40 microseconds or something like that. So quite a bit longer than that, but yeah. But the point that I want to make is, let's look at what happens after half an oscillation. This is the important part, and compare it to what we expect. So this is what is plotted here. So this is these dots over here. This is experimental data. And we do this for 3 different Rabi frequencies. 0.1 megahertz, 0.5, and 1 megahertz. And we can see the expected behavior. You know, we drive stronger and we see more Zeno block. And as the Rabi frequency is slower, then we can see that the block works better. This goes along with the Zeno. But if we try to compare it to basically the ideal simulation, if we relate the drive strength to the measurement rate, and this is these dotted lines over here, so this blue dotted line ideally would lie over here, we see this is very far away. Okay? And this is basically because we're in this non-Markovian regime. The Rabi drive is not negligible compared with kappa. So we're getting a highly reduced effect. Okay? And then this is a big point. Now, what it means for us for this experiment is, you know, for the same drive strength that you would expect a very good block in this non-Markovian regime. I'm saying non-Markovian because it happens because there's kind of some memory to the cavity. It's not dissipating the information immediately out. There is some time scale over here, this 150 kilohertz. But the point is that it still works. Okay, so it's the limited blocking rate, but it still works. And we do this experiment with this limited blocking rate, and we're actually going to use this measurement rate of 1 megahertz. We're going to see that that's going to be enough to show at least a non-negligible effect. So this is one point. The second point that I want to point before actually showing the results of the gate itself are 2 things, and that is dephasing and phase accumulation due to the Zeno drive itself. So let's forget about the Rabi drive for a moment and imagine just a drive that is off-resonant. And if you take a drive that is off-resonant, you can calculate its effect. So this is the density matrix elements and the effect this drive has on all the states in the system. And here I wrote the solution to these to this evolution. So rho as function of t is going to be e to the I mu t of the initial state over here. And in the chi larger than kappa limit, which is the limit that we want to be in, we want separated peaks so we can target a certain frequency to do our Zeno measurement. So this mu here is going to be divided into 2 parts, basically the imaginary part and the real part. Now the imaginary part, you know, multiplied by I, is going to cause a decay. So this part is going to cause dephasing. You could say over here, okay, you know, we get less blocking rate. I'll just increase my drive to compensate for it. But you can't really compensate for it because you're not going to be just measuring this stronger. You're also going to be measuring the other states. So you're going to get this adverse effect of measuring other states, and that's going to cause dephasing in the subspace which you care about. So that is one effect. The second effect, which is even more detrimental, it won't just lower the fidelity, it can actually completely destroy what we're trying to prove. And this is the phase accumulation that you see over here. This phase accumulation, by the way, is familiar to more experts from what is called the RIP gate, the resonantly induced phase gate. This mechanism on its own can apply a really fantastic gate. I think in this paper, I didn't look it up before, I'm sorry, I should have, I forgot, but I think they reached close to 99% fidelity in that gate, maybe 98, I don't remember. It's really a very, very useful gate for such a system. You can just apply an off-resonant drive somewhere and very quickly acquire this phase. Now, the point is that this phase accumulates because it creates entanglement, because if you just have regular evolutions, then this phase between GG and EG, for example, has to stay the same as the phase accumulation between GE and EE, because here we have G and E, and also for these two states. What happens, this phase accumulation has in the denominator deltas over here. And since the tone is separated away from these two differently than from these two peaks over here, it means that this transition, for example, the EE to EG transition, will acquire phase faster than the GE to GG transition. Okay, so this gives us an entangling operation. But remember, we want a non-interacting system. We want to be able to apply a projector that is only doing a projection. We don't want to induce any entanglement in this system. And what this phase accumulation is doing, it's causing entanglement in the system, and it's actually very, very effective and can create a very, very good gate. And what we want to do, we want to get rid of this. And so to get rid of this, what we do is we apply a cancellation signal. We call this symmetric tone. And because our Zeno drive is causing this two states basically to accumulate, these two states to accumulate a phase faster than these two states, if we now apply an additional drive that will cause these two states to accumulate a phase faster than these two states, then now these states are going to be accumulating phase at exactly the same rate. And now our measurement will no longer create this non-trivial phase and will only acquire information and not cause an additional entangling phase. Okay, so let's see that this measurement is indeed trivial. So this is an experiment. What we're doing is we're basically doing a Ramsey experiment on the GG and EG transition and in the GE to EE transition. And what we're doing, we're looking at the frequency detuning, so just a Ramsey experiment. And what you can see here, so the circles, these are experiments. The squares, this is a numerical simulation. And these are the dots and the red and the blue are for the different transitions. And this is basically the phase accumulation. So you can see that when we apply the symmetric tone, then we can see that there is no phase accumulation of the two transitions with respect to each other. It means that there is no induced entanglement. And over here, when there's no symmetric tone, we don't actually have the data. This is just a simulation. We did not take the data here, but you can see that there's this non-trivial phase that causes the entanglement. This is exactly the RIP gate mechanism, which really, if you want to do a gate in the system, you want to use the RIP gate and not this Zeno gate. The Zeno gate just comes to show the universal control. So more on the fundamental level. Okay, so now that we understand the finite cavity line width and the RIP gate, we can, and our scheme is ready to go, and we know that we're just applying a projector, we can actually look at the dynamics of the gate. So this is what the gate looks like. We start by driving the cavity with the Zeno drive and the symmetric drive with this epsilon parameter over here. we initialize the state in a plus state. So this is the density matrix elements. The size of the filling, that's the amplitude, where a fully filled square is 0.4. This is the experiment, and this is a numerical simulation. So after we initialize the state, we turn on our JPA, where we're pumping at twice the FE frequency. So we're actually driving at that frequency, but we're also observing the cavity to see if there was an escape during the gate. And we start also the Rabi drive at a frequency of 1 megahertz. And you can see here, this is the evolution as function of time. After half an evolution, we can see that the EG state is being depleted and has reached the FG state. So this is half a cycle. And after a full evolution, we can see that it came back all the way over here. The largest discrepancy that we can see here in this tomography, so these are quite nice results, and it shows the non-trivial entanglement and what we were looking for. So this is very good and very nice. We can see that there's a rather large discrepancy here between the experiment and the simulation with the FE state, the population of the FE state. Now, what is going on here in this experiment? The way we measure the system is after we're observing to see if there was an escape, we do tomography pulses, and then the tomography pulses map the population to the GG state, and then we do the tomography using a projective readout on the GG state. Now, if there was an escape during the gate, what happens is the cavity gets populated, and that causes, again, the Stark shift, and then our tomography pulses are off resonant. And that means that the mapping of the FE state is wrong in the experimental data. And this is this discrepancy over here. And what happens is that we do a maximum likelihood estimation, and the effect of that is that it takes this population and it spreads it evenly on the population here. So you get an additional identity that is spread over here in the experimental data. And this is why the populations here are slightly larger than the populations over here. Now, the main effect that it does is the following. So we can take this Zeno gate, what we saw is these points over here, and we can apply this for several Zeno drive amplitudes. And we can calculate the concurrence and the fidelity of our thing. And this dotted line over here and these dots, this is the numerical simulation. And you can see that the concurrence agrees quite nicely, whereas the fidelity, the experimental fidelity, is the calculated experimental fidelity is constantly higher. And this is exactly the effect of the incorrect mapping. Okay, so the actual fidelity is something like this, but the incorrect mapping makes it looks like makes the calculation of the fidelity higher than the results. But the important part and the take-home message here is that we have really non-negligible concurrence in the system, and the fidelity that, it's not a fidelity to go, you don't build a quantum computer with this, but it proves the point of universal control in this Zeno subspace. So this is going to be my last slide. And so the last thing I want to talk about is basically the post-selection. So because we're observing during the gate the system, we're looking at it, we can ask, okay, can we actually detect this escape? Can we look at it and detect this escape? Now, the system, we had to design it such that chi is much larger than kappa, but also we can't make kappa too large. If we make kappa the rate of the cavity too large, it will affect mostly the coherence times of the qubits, but also there will be the extra dephasing effect due to the Zeno measurement itself. So there's this whole interplay, and you actually need to make kappa not too large in this experiment, and this is why kappa is 150 kilohertz. But our gate was also, it was done with a 1 megahertz Rabi drive. It means that the gate itself takes 1 microsecond. And this is the time scale of kappa also. This is the ramp up time of kappa. It means that if you look at the voltage, there is no immediate escape. And this goes back to the question relating to your experiment, Zlatko. You can't immediately catch the escape. All of this voltage thing that you might imagine is actually blurred. Okay, it's filtered out by the cavity. It's like a low-pass filter over this 1 microsecond. And you can basically do an experiment to ask yourself, how well can you do and how well can you do a post-selection in the system? And what we do, we basically do this experiment where we're putting the system not in the FE state. Here we specifically initialize it in the EE state, and then just measured. And this is this histogram over here. And this simulates a block, right? You started in the EE and the system was blocked, basically. And this is the signal that you would get, or the histogram of the signals, the averaged signals that you would get. And then we simulated an escape. Basically, we initialized the system in the FE state. And then we just started the measurement. And this is the best case for an escape, because your best chance to measure an escape is if it happens immediately at the beginning of the gate. And this is this red histogram over here. Okay, you can see that it's this kind of wonky distribution. It really should be in an ideal system with very long coherence times and everything nice. It really should be like a peak that sits somewhere over here. But also, this F state has a relatively short lifetime, was about 13 microseconds. So a lot of the time, or a non-negligible amount of time, you get a T1 event. So this is being filtered, and also there is a T1 event. So you get this kind of like wonky distribution, and the fidelity isn't fantastic to distinguish. But you can always just take this data, and this is this gray curve. So the gray curve is basically the distribution of the actual Zeno gate experiment that we did. And you can see that it's kind of shifted over here. And then we can just take this data and post-select. So basically you decide on a certain threshold, and you post-select more and more, and you can calculate the concurrence and fidelity. And indeed, we see that as we post-select more and more on these events, the concurrence actually goes higher and higher, and also the fidelity of the gate goes higher and higher. So this escape kind of corresponds to us actually seeing, okay, this is probably a real escape, not just some noise. Of course, as you get closer to 100%, the error bars become larger and larger, because there are very rare events that escape in such a way. Okay, and I'm pretty much finished. I'm done. I hope that I've convinced you that the Zeno effect is interesting. Also on the trying to set it up level, and also on the hope I showed that it shows universal control, and I hope that I made you think a little bit about some philosophical aspects of it, and arouse some controversial discussions about this. And finally, I'd like to thank the whole team that worked on this: Lee, Philippe, Daniel, and Brigitte, who did the theory, and the experimental group over here. And thank you for listening.
All right, thank you, Shay, for the awesome talk. Congrats to you and the lab on the very nice results. Maybe you've kind of touched on this already, but question from the audience from Adarash: how do you calibrate the Zeno gate?
What specifically do you mean by calibrate? I mean
I presume the context is in the context the CNOT part, I think.
How do you? I mean, we do all the calibrations before. So basically, you calibrate epsilon before, you calibrate your Rabi drive before. All this is done. So you start the Zeno drive, and there's a start shifted frame. Of course, you have to do this in the start shifted frame, and then you apply your drive, and then at the end you do the tomography. I mean, maybe I didn't understand the question, but
yeah, I'm gonna
there's a lot of calibrations here. There's a lot of calibrations here, so I maybe need to be more specific. Calibration of what? But we calibrate everything separately. The chi's of everything separately, the drives the drive strength epsilon. What is epsilon? We calibrate that separately by doing a Ramsey experiment on the EF transition and so on. So every little part here has its own little calibration method.
Sweet. Yeah, and I'm going to guess here because I don't know exactly what the question is. Feel free to clarify in the chat. I'm going to guess the question's coming from thinking about some of the calibrations on let's call them normal gates as opposed to Zeno gates, where oftentimes you have to tune some amplitude of the gate, and you might do that by repeating the gate many times and looking at some
Okay.
sequence.
So you're talking about optimizing. So here we did not try to optimize for maximum fidelity. Okay. Our point was to show that there is, a non-negligible concurrence.
Because it could be that you were just a little bit off in something, in something. How I guess you're saying we just didn't worry about that.
Often in what sense? I mean, the frequencies are spot on because we calibrate all those things. And we also follow everything up with a full numerical simulation. So to verify everything, I think I have it somewhere here. Where is that? I should have, I guess here, all right? So we actually simulate the full system over here. So this is the master equation for the full system. So this is the decay channel of each qubit. This is the dephasing of each qubit, and we take into account all of that. And we even take into account the self curve of the cavity into that, and we verify things with numerical simulations to see that they all add up and match up. And at the end, it's a small system. And at the end, what this master equation does is it takes the cavity as part of the quantum system, and now, just there's a little kappa that's going onto the outside. This again relates to the original discussion. What is the measurement device? Okay, and now, so it takes this complex dynamics. Oh, now I've put in, the cavity in there. Now the dynamics are much simpler. Okay, and they're so simple you can numerically simulate them. But
and these are Lindblad simulations, I take it. Yeah, these are Lindblad, right?
Yes. Yes.
Yeah.
These are Lindblad simulations. All done numerically. And with regards to the fidelity, also I want to mention that this is not the average fidelity. So typically people will quote average fidelity for a gate. This is important for quantum computation. The fidelity here is the fidelity to reach the Bell state, basically, after the gate. Lee basically showed nicely that it is a very, very good proxy, almost a perfect proxy for the average gate fidelity. But and also an experiment just to verify, we initialized in different states and applied the gate in different states, just to make sure that we understand everything and everything works for many initial states. At the end, we were focused on seeing something. There's some finite concurrence and fidelity. But there was a lot of calibrations to make sure that we're not fooling ourselves with anything.
Sweet. And folks, feel free to post any final questions here, or if I missed your question earlier. I think we had one from Shay earlier that said, can you comment on, well, I guess maybe this is not the point of the experiment, but for generating entanglement on this Zenodynamics, maybe not here, but more generally, your perspective on generating entanglement with Zenodynamics versus, say, other types of protocols.
Yeah, so the Zenodynamics, when you present the concept here, right, especially over here with the multi-qubit, it looks like some magical thing where I can entangle 100 qubits with just like some single operation. Okay, but with the Zenodynamics, the trick is always, usually with the Hamiltonians, the trick is how do I induce the interaction in an efficient way. With the Zenodynamics, you're hiding the interaction in the measurement, and you're saying, okay, I just need to do a measurement. Okay, And even in this scheme, it looks like, and in all these Zeno things, the measurement looks, oh, I'm just observing this level. But this observing this level is highly non-local. It is a very, it's not a trivial interaction, okay? It is a very difficult interaction. And so it might, when you first look at it and you're like, look, oh, this might be a very good way to attain, a 100 qubit gate immediately, very fast and everything. But when you go down to the details, you got to ask yourself, what is the interaction behind the measurement? And the fact that we're hiding it behind a simple word measurement is maybe makes it sound simple, but it's not simple. It's how do you construct that measurement apparatus that creates the interaction that you want? I mean, this was the meat of this experiment and the meat of such Zeno experiments, right? How do you create this measurement that you want, this interaction that you're calling measurement? So measurement is a form of interaction that is non-trivial.
Awesome. Great. Well, seeing as we're almost 20 minutes over with all the questions,
okay.
Maybe I'll leave you to say any final words you want to share with us before we close.
I want to say that, we have positions in the group if anyone wants to come over, short fellowships, longer fellowships, however you want. You feel free to contact me. You can just type in Google SQC Lab and you will find us. And I really hope you enjoyed this talk, whether it was the details or just the nice concepts behind this Zeno thing. All right. Hope it wasn't too controversial with the measurement is an illusion.
Well, I truly enjoyed it. Thank you, Shay, for the great talk. Congratulations on the very nice results from the lab. Thank you all for watching and for the great questions throughout the talk. Tune in next week, same time. This talk will stay recorded, so you can go back and rewatch it. But otherwise, we'll see you every Friday at noon Eastern Time.